Hello, and so in this video we're going to be continuing our work with Hooke's law, but now we're going to consider some movement. So basically we're going to be considering acceleration. Okay, so last time we looked at examples like this. So we had, let's say, a string hanging down and then a little particle, a little ball at the end of it. And so the forces in this case, well, there's going to be the weight mg of the particle, but then the tension upwards because it's been stretched, right? The string is being stretched down, which means the force to oppose the stretching has to act the other way upwards. Okay, so we've seen that last time, and so then in this case there's no acceleration, so that means when we resolve up and down, well, the upwards force T has to equal the downwards force mg. Okay, so basically we looked at forces in equilibrium, pretty much. So the opposite forces equal one another. But really what we're going to now do is involve acceleration. Okay. So again, we've got the same scenario. So the weight mg, and then the tension upwards T. Now there's going to be acceleration. So let's say the acceleration is going to go up, right? The ball's going to ping up, right? So now there's acceleration A. So now that means then when we resolve up and down, well, we have to handle this with a bit of care, because let's take acceleration to be the upwards direction. Okay, so the upwards force is T. I have to subtract by the opposite downwards force, which is again mg, and instead of equaling 0, it's now going to equal ma. So this is basically F equals ma, right? And that's really it. Okay, so we're just going to consider acceleration, but the calculations pretty much remain the same. There's not much of a step up. So we're just going to continue looking at some examples, right, with involving acceleration here. So we've got this question here then. Firstly, so we have a particle of mass 4 attached to one end of a light elastic string PQ. The natural length is 0.5. The modulus of elasticity is 40. The spring rests on a smooth horizontal plane with the end Q fixed. The particle is held at rest and released. Find the initial acceleration. Okay, so firstly PQ is 0.8 meters. Okay, so what is going on here? What do I draw? Well, the key detail that helps me visualize what's going on is I'm told the spring is on a horizontal plane. So a plane is basically, again, like a fancy word for like a surface or floor, something like that, right? So it's on a horizontal sort of floor, okay, horizontal surface. So it's going to look a bit like this, right? There we are. So it's a completely flat sort of surface, right? And so my spring is on it, so it's going to look like this, okay? And there we are. Okay, so firstly, the fixed point is Q. So Q is going to be here. And then at the other end is where my particle is at P. Okay, hopefully happy with this. Now, the best thing to do is to consider the lengths first. So firstly, I'm told that PQ is 0.8. So from Q to P is 0.8. Okay. So in other words, that's the total length of the string, right? But what I'm also told is the natural length is 0.5. So basically like the original length before we add anything onto the string, the normal original length is 0.5 pretty much, which tells me the string goes from 0.5 to now this 0.8 meters. What does that mean? Well, this that means it has to have been extended and stretched. Okay, so the natural length, I'll mark it here, 0.5, and then therefore the string must be stretched by a further 0.3. Okay, so my extension X then is going to be 0.3. Okay, hopefully happy with that. Okay, it's a stretch because the string has increased in length from the natural length. Okay, And so so this is helpful because it actually tells me about sort of like if about the force in the string, because I know it's going to be a stretch. Then it's an extension, it's a stretch. So because it's a stretch, the particle's causing a stretch, right? That means the string is going to stretch forwards towards the particle, right? The string must be being stretched forward. So that means the force in the string has to then act the other way to oppose the forward stretching. So the tension force acts backwards, right? Again, we went over how the forces work in the first part. So so hopefully you are sort of confident in that. Again, we went over that in the first part. If you need a recap, I'd advise watching that. But there we are. So that's my tension force, okay, opposing the stretching forwards. Hopefully happy with that. Obviously, the particle will have a weight. Well, the mass is force at before G, but because we're only horizontally, because we're only in the horizontal, we don't care about any vertical forces. So there we are. That's all. That's everything there. Okay. Now, the last thing we need to do is actually we also need to consider the acceleration. Okay, so I've got this visual here to really help you see what the motion, the movement is going to look like for the spring and the particle here. Okay, so here you can see I've got this blue spring and then a pink ball at the end of it. Now I want you to imagine we're holding the ball with our hands, right? And so I want you to imagine we're going to keep pulling and stretching it further. So you can imagine we're pulling the ball, the pink ball further and further and further, stretching the spring further and further until this point. Okay, so at this point we're still holding the pink ball to stop it moving. Okay, but now I want you to imagine we're going to let it go. Okay, at this point we're going to let it go and let it move naturally. Hopefully you can imagine what will happen then. So if I play it, this is what it's going to look like once we let go of the ball. Okay, and there we are. Okay, so it's so because it's been stretched and stretched, once we let go, the spring is going to start to compress and go backwards. Okay, so the ball is going to start moving backwards. Okay, hopefully you can see that, right? So it's been stretched and stretched. Once we let go, it's going to want to naturally compress itself and go backwards. Okay, that's the visual there. So hopefully that really helps you see what is going on here. Okay, hopefully that visual has helped. Again, if you want to see it for yourself, the link there if you want to, if you want it. But hopefully you can see, because in this example, again, the spring is being stretched forwards, again, because of this particle. It's the exact same scenario. We're holding the ball at rest. We're told the particle's held at rest and then released. So we let go of the ball, exactly like we just saw. So again, like we just saw, once we let go, the particle's then going to start to move backwards. We're going to start to ping back. Okay, so therefore we can assume the acceleration is going to move to the left. Okay, to move backwards. Okay, that's the direction of my acceleration. Okay, so hopefully you can see that. Hopefully that visual's helped see that's what the movement will look like. Okay, now. Okay, so now we need to find the acceleration then. Well, if I now then resolve forwards and backwards to the right and left, well, so my tension force is here. There are no other horizontal forces. So actually T, which is in the direction of acceleration, T has to equal ma, where the mass is 4, so 4 lots of A. Okay, hopefully happy with that. And then we can also find T, the tension, by using Hooke's law. Right, which is T is lambda x over L. So that means T is, well, the modulus of elasticity is 40 times the extension x, which is 0.3, divided by the natural length, which was 0.5. And so we calculate that, we get 24. Okay, and that is my tension. But now I can sub that in here to find A. So 4A is going to be 24. Therefore A divided by 4, I get 6. And there we are. That is my acceleration there. Okay. Now, hopefully happy with that. Okay, so that's going to be 6 meters per second squared to the left. Okay, that's my acceleration. Now, suppose you couldn't visualize that, or you're struggling to see where the movement is. Sometimes we don't know for definite what the movement's going to look like, where exactly the particle's going to go, left or right. Let's assume instead of deceleration acting to the left, let's assume we pick deceleration to move to the right instead. The particle's still going to move forward. Let's say. So, if we did that, okay. So, if we did that, if we weren't too sure about where to put the acceleration, that's fine, because if we were to resolve right and left in this instance, okay, well, in the direction of acceleration, tension is now opposite direction, so it's going to be minus T equals A, equals 4A, right? So that's F equals MA again, but now the tension is in the opposite direction, so it's negative. Well, the tension is still going to be 24 via Hooke's law, so that means that 4A is now going to equal minus 24, so A is minus 6. Well, it's the same number, but it's a negative. But don't freak out about that, right? Because if it's negative 6, right, that means if it's negative 6 to the right, then we can just flip the direction, and then it will turn to be a positive. Okay. So the negative means it's in the opposite direction. So indeed, this tells me that it's still 6 meters per second to the left. Okay. So if you assume that the acceleration to be in the opposite direction to the right, you'd get a negative answer. But then you just flip it in the other direction to make it positive. So either way, you should be able to conclude the acceleration is to the left. Okay. So do not panic too much if you can't visualize that, okay? The calculation should pretty much tell you if what direction the acceleration is in. But what you do need to make sure, and it's very important, is you get your forces in the right direction, okay? It's okay if you don't know where the acceleration is. Again, sometimes we don't know exactly where it's going to go, but we do need to know where the forces are going to go. Okay, so there we are. Okay, so if you're struggling to visualize where the acceleration is, that's not a problem, as long as my forces are labeled correctly. Okay. Now, with that in mind, now part B is telling us, well, it's the exact same scenario, but now PQ is 0.4. So again, we're on this horizontal surface. We've got this string again. Again, we've got the particle at the end of it, Q to P. But now the distance is 0.4. Okay, this is where the length is, again, very important, because the natural length, again, is 0.5. Well, hang on. The natural length, or the original length, is 0.5, but now the string, the length has gone to 0.4. So the length has been shortened, which means in this case it has to be a compression that's going on. Okay, so that's very important. The lengths, if you pay attention to them, tells me if it's a stretch or a compression. Okay, right. So that means because it's being compressed, the particle is sort of pushing into the string in this case. Okay. So the compression is acting to the left here. So that means the force in the spring here has to act to the right to oppose that compression. Okay. And so this again will be my force T. Technically it'd be a thrust force now, because thrust is when it's compressed. Tension is when it's stretched. Okay. Hopefully happy with that. Okay. Hopefully happy why it's a compression and therefore why the force in the spring has to act forwards to oppose the compression inwards. Okay. Now, that's really it. Again, I can work out my compression, which I call X. Well, the natural length or the original length was 0.5. It's shortened to 0.4. So that means the amount compressed has to be 0.1. Okay. I've got my visual here again. But this time, instead of stretching the pink ball forward, I'm going to be compressing it and pushing it further into the spring. So what's happening is now we're sort of pushing the ball into the spring to compress it. So it's going to look like this. We're going to be pushing it into the spring, compressing it further and further. Okay. And then we leave it there. Right, and so you can again still imagine we're still holding the ball here. Okay, now where do you think the movement's going to be now once we let go of the ball here? Okay, and hopefully you can see what will happen. Visualize it in your mind. But here we are. So what's going to happen once we let go of the pink ball? Again, imagine we're holding it with a hand still. Once we let go of it, let it move naturally. What will happen? It's going to ping forward. Okay, the spring is now going to stretch itself and ping the ball forwards. Okay, hopefully that makes sense. And so you can see that clearly there. Okay, but that's what's happening here. Okay, so hopefully again that visual has helped. So now again, as we discussed, the ball is compressing the spring here. So it's going to move like that visual, right? So once we let go of the particle, it's what we expect to be. It's gonna spring and move forward. So now the acceleration is going to move forward here. Okay, it's going to move to the right. Hopefully happy with that. Okay. So if I now resolve up and down, left and right. Okay, well, I've got my force T. That's going to equal MA, which again is going to be 4A. Okay, but of course I can also use Hooke's law to find T. Okay, well, T is going to be, the modulus of elasticity is 40. Times X. Now X is the compression now, which we said was 0.1, divided by the natural length 0.5. So that will get me 8. Okay, so T is 8 here. So now again I can sub T into here to find A. So 4A is going to equal 8, therefore A is going to be 2. So there we are. So my acceleration is 2 here. And indeed, it moves to the right. Okay, it moves forward. Again, if you, weren't too sure about the movement, that's fine. If you assume the acceleration was acting to the left, the other way, right, you would have, again, minus T, because T would act in the opposite direction to acceleration. Minus T before A, so 4A would then be minus 8. So A would be negative 2. So you would get the negative answer, which would mean, because it's negative, you'd have to flip it in the opposite direction. So either way, you should get the acceleration to be 2 in the forward direction. So hopefully that you're happy with that and that makes sense. But there we are. So we have this question here now. So here we're told a particle of mass 2 is attached to one end P of a light elastic spring. The other end Q is attached to a fixed point O. The spring is natural length 1.5, modulus of elasticity 40. The particle is held at a point 1 meter vertically above O and released from rest. Find the initial acceleration of the particle. Okay, so firstly, again, we need to draw a picture. Now, what's happening here? Okay. So again, we're told at one end of the string P is where the particle is. And the other end Q is at a fixed point O. So basically Q is O. Okay. I'm also told the particle is 1 meter above O. So actually, if O is my fixed point, right? So O here, the particle is actually above O. So it's actually going to look like this. So instead of hanging down, it's sort of being up instead. So this is O, and then that's P here. Okay. And so this is 1 meter. Okay. So hopefully happy with this. Okay, I know it's quite an unusual diagram. We haven't seen an example like this in the last section, but hopefully happy with that. Okay. So okay. Now, okay, I'm going to need to label my forces. Well, again, the particle is going to have its weight going down. Okay, again, so there we are. Now the mass is 2, so it's going to be 2g. Okay, that's the weight going downwards. Okay, and then what about the force in the spring then? What about the force T? Now, well, actually, we can just use the lengths to tell us if it's a stretch or a compression. That will help us. So we're told the natural length is 1.5. But actually, in this case, the length of the string is 1. Okay, so the natural length or the original length is 1.5. So that means the string has compressed because obviously the length has gone down. Okay, so it's a compression here. Okay, this is again why it's so important to pay attention to the lengths given. So we can work out it's a compression because again the length of the string has gone down from the natural original length. Okay, so again that means the particle is sort of pushing into the spring, which makes sense because the weight is acting down, so it's going to push into the spring, which means to oppose the downwards compression, then it's going to then the force is going to act upwards in the spring there. Okay, hopefully that makes sense. Okay. Okay, and by the way, just to be crystal clear, it's the particle causing the compression. So which means it's being compressed downwards. Okay, anyway, so there we are, hopefully happy with that. Lastly, we need to consider the acceleration of the particle. Okay, now well, you might look at this and think, well, the particle's going to drop down. Okay, it's going to come down. Okay, let's work with that. Let's say the acceleration is acting downwards. Okay, I don't know for definite, but I can confirm if it's true or not at the end of my answer. Okay, so okay, let's work with that. So if I resolve up and down, well, firstly, so deceleration is downwards. So firstly, my downwards force is 2g. Take away the opposite upwards force, which is t, equals ma, right? So the mass is 2, so it's going to be 2 lots of a. Right, okay. So there we are. Now, of course, we can also find the tension. It'd be a thrust, wouldn't it? Because it's compression. I can find the thrust force T using Hooke's law. So lambda x over L. So, well, firstly, lambda is 40, the modulus of elasticity, times the, well, it wouldn't be extension, it'd be compression, wouldn't it, in this case? Now, the natural length is 1.5, but as we can see, it goes down to 1, the length of the string, which means the compression, which is x, is going to be 1.5 take away 1, which is 0.5. So that's how much the spring has been compressed by. Okay, hopefully that makes sense. And so that means it's 0.5 for the compression divided by the natural length, which is 1.5, and then I can work that out. and I get 40 over 3. And there we are, that's my fourth t. So I can sub that in here, so that means 2g, which is 2 lots of 9.8, minus 40 over 3 for t equals 2a. If I simplify this, I get 2a to be 94 over 15. Therefore, a is going to be 47 over 15. Or as a number, that's going to be 3.13 meters per second squared. So that's my acceleration. So there we are. So the acceleration is positive, which means indeed it is downwards. Okay. So that's, there we are. So that's going to be 3.13 meters per second squared downwards. Again, if you instead assumed perhaps the acceleration's upwards, you'd get minus 3.13. So you'd have to flip the acceleration downwards to make it positive. Okay, so either or, no matter what direction you took, you should at the end confirm it's going downwards. Okay, so there we are. So it wants me to state the magnitude and direction of the acceleration. Now the magnitude just means the physical number. Okay, so the magnitude is simply 3.13, and the direction, as we discussed, it's downwards. And so there we are. Okay. Again, just to emphasize, if you got a negative answer because you assumed acceleration was going up, the magnitude is still 3.13, but then the direction is downwards because it'd been the opposite direction if it was negative, so it'd flip downwards. Anyway, that's my acceleration. Okay, 3.13 downwards. Okay, so we're going to be looking at some more questions. So here we're told a particle of mass 0.8 is attached to one end of a light elastic spring, natural length 2 and modulus of elasticity 20. The other end is attached to a fixed point O on a smooth plane inclined at an angle alpha. The particle is held 1.6 meters down the slope from O. It's released from rest, so we need to find the initial acceleration. Okay, so first of all, if I just redraw the diagram there, make it bigger, make it clearer. Okay, so we've got this spring, so it's at a fixed point O. So O here, up the plane, and then the spring it then moves down like this. Okay, and then we have a particle at the end of it. Okay, there we are. I also know that the distance is 1.6 meters. Okay, the whole spring has length 1.6. Okay, then I need to consider my forces. Well, firstly, again the particle is going to have a weight. Now the mass is 0.8, so it's going to be 0.8 g. But of course, with these slope questions, we also need to split up the weight like this. So this is going to be so if this is alpha, that's going to be 0.8 g cos alpha, and then here 0.8 g sine alpha. Okay, and then of course we're going to need to consider the force in there'll be a reaction force, my apologies, that way, and then we need to consider the force in this spring. Okay, now again we don't we should look at the lengths. We don't need to actually guess if it's stretching or compression, because we're told the lengths. We obviously know the total length is 1.6, but we're told the natural length is 2. So the original length is 2, but then the spring goes to 1.6 meters. So it's a compression by 0.4. So that means it's a compression, and the compression, which is x, is going to be the natural length, or the original length if you will, take away the total the length here, which is 1.6, And so that will be 0.4. So it's the spring here has been compressed by 0.4. Again, very important to pay attention to the lengths here. It will tell you if it's a compression or stretch. And so because it's a compression, the particle's still effectively pushing into the spring, okay, to compress it. So because the particle's sort of pushing into the spring, it will then have a thrust force or a force the opposite way there, okay, force T. That's important. If you just looked at it at first glance, you might think, well, the particle is stretching the string downwards, but that's not what's happening. It's actually in compression because the length is still shorter than the original length. That is very important. And so there we are. So the force acts downwards because again the particle still effectively pushing upwards into the spring. Okay, so that's why it's important to pay attention to the lengths. So we got so there's my force again, T there, and so they're all my forces then. There's no friction involved here, by the way, simply because it's a smooth plane, it's a smooth surface. Remember, smooth means no friction, so there's no friction involved here, okay? No friction between the particle and the surface, okay? So then we need to consider the acceleration. So you might think, well, the particle is now going to move down the slope, okay, like this. Let's assume it is then. Let's assume the acceleration is downwards. Again, I don't know for definite, but let's assume it is. Let's assume the acceleration is downwards. So if I now then resolve up and down the plane, up and down the surface, up and down the slope. Okay, well, let's if we look at the acceleration's downward, so let's have a look at the downward forces. Well, firstly, we've got my my force T, but also then this weight component 0.8 g sine alpha. So that means T plus 0.8 g sine alpha. And actually, there's no forces acting upwards. So actually, that equals ma. So that's equal the mass, which is 0.8 times acceleration a. Okay, hopefully happy with that. Now, we can also find T via Hooke's law. So T is lambda x over L. So T, well, the modulus of elasticity is 20 times the compression, which we discussed, is 0.4 because the natural length was 2, but then the length is now 1.6. So a compression of 0.4. So therefore the tension, if we work this out, is going to be 4. So that's my thrust, sorry. My thrust is 4. So I can substitute it into here then, right? So that means 4 for T plus 0.8 G, which is 9.8, lots of sine alpha. Is 0.8 A. Now actually sine alpha, we can also work we can work out a value for sine alpha because we're given tan alpha is 3/4, right? So again, if we look at SOHCAHTOA, hopefully you're quite familiar with this sort of trick, right? Here, so what we can do is, well, if we literally look at this part, we can deduce that if we draw a triangle with the angle alpha, the opposite is 3, so the numerator, and then the denominator is 4, so that's my adjacent side. Therefore, the hypotenuse turns out to be 5 because that's Pythagoras, right? 3 squared and 4 squared rooted is 5. So therefore, I can work out sine alpha because that's opposite over hypotenuse. The opposite is 3/5. And there we are. That's sine alpha. Okay. So that means sine alpha is 3/5. So that means I can multiply here by 3/5. So therefore, if I simplify all of this, I get 0.8 A to be 8.704. Therefore, divide by 0.8, I get A to be 10.88 meters per second squared, and that is my acceleration. Okay, and again, the acceleration is positive, which confirms indeed the acceleration is 10.88 downwards. Okay, so that is true. It is downwards. So there we are. Okay, then we've got this question here. So here I'm told a particle of mass 1 is attached to one end of a light elastic spring of natural length 1.6, modulus of elasticity 21.5. The other end of the spring is attached to a fixed point O on a rough plane, inclined at an angle alpha. The coefficient of friction is 1/2. Particles held at rest at a point 1.2 meters down from O. The particles released from rest move down the slope. Find its initial acceleration. Okay, so it's going to again be very similar to the last question. So we're still on a slope. So again, it's going to look a bit like this. Okay, at an angle alpha. And so then my spring, so it's at a fixed point O, and I'm told the particle is moving down the slope. So my fixed point here has to be at the top. Okay, then the spring has to come down, and so then my particle obviously moves down the slope like this. Hopefully happy with that, the orientation there. Again, then if I label my forces, again there's going to be the weight of the particle. Now the mass is 1, so 1 times g is just g. Okay, that's my weight. Again, I'm going to split up my weight like this. So this is going to be, if this is alpha as well, this is going to be g sine alpha, cos alpha, sorry. And then here, g sine alpha. Okay. Of course, we're also going to have a reaction force, R, like this. Okay, and then we need to consider the force in the spring. Again, to help us work that out, we need to consider the lengths, okay? We know the natural length is 1.6, and we're told the particle is 1.2 meters away from O. So that means this distance here is 1.2 meters, okay, between O and the particle. So if the natural length is 1.6, the original length, and the length has gone down to 1.2, again, it has to be a compression. The length has gone down, okay? And so the compression again, which is x, that's going to be the natural length, which is 1.6, take away the length here, which is 1.2, so 0.4. That's my compression, okay? So the spring has been compressed by 0.4. So again, because it's a compression, again, effectively the particle then has to be still pushing into the spring. So then the spring, the force in the spring will act the other way here, okay, to oppose the compression. Right, and of course, actually, with this question, the key difference with the last one is there's friction involved now. Okay, there's friction because it's a rough plane. Rough means there is friction. Okay, so where's friction going? Now, actually, this time we know actually for definite the acceleration is downwards. Okay, so the acceleration A is down the surface. Why? Because we literally told it moves down the slope. So if we told it moves down the slope, the acceleration has to be downwards, okay? There's no guesswork needed there, okay? So there we are, we know for definite it moves down the plane. If it moves down the plane then, so the particle moves down, then the friction would have to act up the plane, okay? So there we are, that's my friction force. Okay, so that's all the forces labelled. So now we can proceed by using some equations. So firstly, if I resolve, I'm going to have to resolve in both directions. So let's firstly resolve perpendicular like this. So firstly, the force R take away the opposite force, which is going to be this G cos alpha. That's going to equal 0 because there's no acceleration in this direction. Okay, the acceleration is down the slope, it's not perpendicular. Anyway, no acceleration in this direction, so that means R is going to be G cos alpha. So that means R is the reaction force is 9.8 times cos alpha. Now again, we can work out an expression for cos alpha because we know that tan alpha is 5/12, which means if we do a little triangle, so the opposite side has to be 5 and the adjacent has to be 12. So then if we do a bit of Pythagoras, 12 squared and 5 squared, the hypotenuse is 13. So there we are. Okay, so therefore we can deduce that firstly cos alpha is going to be the adjacent 12 over the hypotenuse 13, and also sine alpha, which is the opposite 5 over the hypotenuse 13. Okay, well there we are. Well, we know that cos alpha firstly is 12/13, so we can times by 12/13 here, which gets me R to be 9.05. Okay, and there we are. Then I'm also going to resolve in this direction, so up and down the surface now, up and down the slope. So firstly, well, the acceleration is downwards, so let's treat downwards as the positive direction. So the force is downwards firstly, down the slope. Well, firstly this T force, the thrust, right? And then we also got this G sine alpha acting in that direction. And then we're going to take away the friction, which acts the other way, right? The friction acts upwards instead. And that's going to equal mass times acceleration. Well, the mass is 1. So it's literally going to be A. Okay, just the acceleration A there. Okay. So if I simplify this, I get T plus G sine alpha. So that's going to be 9.8. Now we know that sine alpha again is 5/13. Take away F is A. Okay. So if we simplify this even more, that's going to be T minus F plus 49/13 equals A. Okay. Now, obviously then, to find the acceleration, we're going to need to find the friction force F and the thrust T. Okay, well, firstly, let's find the thrust, the force T. Again, that's going to be lambda x over L. So that means T, well, my modulus of elasticity is 21.5. Times x. Now x is the compression, which we discussed was 0.4, right? Divided by the natural length, which was 1.6. Okay, so we can work out the force T, which will be at 5.375, and there we are. But of course we also need to find friction in order to find A. I can also then do F equals mu R, right? Because I also know my coefficient of friction is a half. Okay, so mu is a half. So that means F is going to equal a half times the reaction R, which was 9.05. So that would mean F would be 4.5 4.525. And there we are. Okay, so now we've found T and F. We have the ingredients to work out the acceleration A. So again, we can use this formula here. So that means A is going to be T minus F. So that's going to be 5.375 take away 4.525 plus 49 over 13. Okay, so therefore if we work all that out, I get the acceleration A to be 4.62. Okay, and there we are. Then part B, we've got this one marker that says, without doing any further calculation, state how your answer to part A would change if the coefficient of friction was greater than a half. Okay, so again, this coefficient of friction. Now, if mu was greater than a half, I'll do it here actually. If mu was greater than a half, well, what we can deduce from that, the only equation that involves mu is again F equals mu r, right? So if mu is greater than a half, then the friction has to be bigger. So friction is bigger. And so then how does that affect the acceleration? Well, again, as we can see here, in this equation, the acceleration, we're taking away F. So if F is bigger, that means we're subtracting a bigger number here. So that means A would have to decrease, okay? And there we are. So that's therefore the acceleration would decrease, so my answer would be lower. Okay, because indeed my answer is deceleration. So there we are. Okay, so you can reason it like that. You can just literally just look at the equations and then see. You can reason mathematically in that way. Okay. Okay, so we've got this question here. So here we're told a particle P of mass 2 is attached to the midpoint of a light elastic string of natural length 0.4, modulus of elasticity 20. The ends of the string are attached to two fixed points A and B on the same horizontal level with A being 0.6. Again, they tell us basically everything in the diagram here. So if I just copy the diagram out, make it a bit bigger. So we have point A here. Then it comes down, and then we have a particle P here, then it comes back up to B, and so there we are. We also know that the lengths, well, either side, A to P, the length is 0.5 meters, and also from P to B is also 0.5 meters, okay, which makes sense because we're told P is in the midpoint. So in the middle. So there we are. Okay. So what's essentially happening, again, we looked at an example like this last time, but it's basically a slingshot. Hopefully you can see that right. I've got the diagram here to visualize what's going on. Hopefully you can see then that the sort of ball, this particle, is pulling the string downwards like a slingshot. So basically the string, the total string, again from A to B, this is my total string. So it's A to P, then P to B. So basically the string is sort of split into half. Okay. Hopefully you can see that right, into two parts, A to P, then P to B. So these two sides are my two parts of the string. Okay. So that means the total length of the whole string is going to be it's going to be 0.5, add the other 0.5, right, to get me 1. And there we are. So hopefully that makes sense. So that's the situation, right? Okay. Now, let's think about forces. Okay, so firstly, again, the particle is going to have a weight. Okay, and that's going to act downwards. Well, the mass of the particle is 2, so it's going to be 2g. Okay. Then we also then need to consider the force in the string. Now again, the string is split up into 2. Again, these 2 parts, the 2 halves, A to P, then P to B. So there's going to be tension in either side. Okay, in the left and the right side. Now, we need to confirm now, is it a stretch or a compression? Well, you might assume it's a stretch, but let's verify that. We're told the natural length of the string is 0.4, but as we worked out, the total length is now 1, so the string has gone from 0.4 to 1, so that means it's a stretch. Okay, which means then the extension, that's going to be x. That's going to be the total length take away the original, which was 0.4, to be 0.6. So the string in total has been extended by 0.6. Okay, hopefully happy with that. And so that means indeed the strings have been stretched. So firstly, the left side is again being stretched towards the particle. So that means the tension is going to act up like this. The same story from the right side. So that's so the stretch is going to be again towards the particle, which means the tension acts up like this. Okay, and the forces are going to be equal here because it's symmetrical, because P is in the middle. Okay, so the strings are equally split on the left and right, so the forces will have to be the same. Okay, there we are. Now, if we then add on the other length, so hopefully happy with that. That's the situation here, okay? If I then, we also know that this length from A to B is 0.6. Okay? Now, the issue is the tensions are on a slope. What we need to do is then put the tensions vertically and horizontally. So if we do it like this, okay, then what we can do is split up firstly the tension here on the left. Well, if we're going up like this, we can go vertically up here, then to the left here. Okay. Right. Now, let's say now we're going to need an angle. Okay, so let's call this theta. This is 90 degrees, right? My right angle. This force then is going to be T sine theta. And this force here, and then this here is going to be T cos theta. Okay. Again, we don't know what theta is, but that's okay at the moment. Now, because P is in the midpoint, this angle here is also going to be theta as well. It's going to match the other side. So again, if I now sort of deal with the T on the right here, that's going to act up here. Again, we can go up like this, which should also be T sine theta. And then to the right like this. And that'd be T cos theta again, right? So there we are. Okay, so now there we are. So of course then we're gonna have to find theta. Okay, we're gonna have to find theta. But again, because P is in the midpoint, we can actually split up the whole length A to B 0.6. We can split this up to 0.3 each way. Okay. Now what we can do to find theta? Well, we also know the lengths here and here. Let me, if I do it in a different colour, let me just, let's take one of these triangles here. Let's take this left triangle here. I'm going to copy it down here. So this is theta, right angle. We know that this length the hypotenuse here, that's going to be 0.5. And this length is 0.3. Well, hang on, we got two sides in a right angle triangle. We can use SOHCAHTOA to find theta. Now, this is my hypotenuse, and this is going to be my adjacent side up here. So we're going to use cos. So cos theta is adjacent over the hypotenuse. Well, the adjacent is 0.3 over 0.5. So that means cos theta is 3/5. Okay. Now, actually, we could then just proceed to find theta, but we don't really need theta on its own. All we need is sine and cos theta. Okay, we don't need theta on its own. Now, I know that cos theta is 3/5. Okay. So if I now find this side here, by using Pythagoras, so that's going to be 0.5 squared take away 0.3 squared. That would get me my opposite, which is 0.4. Okay, so 0.4. Now I can work out sine theta, which is opposite of 0.4 over the hypotenuse 0.5. That simplifies to 4/5. Okay, so now we have an expression for cos and sine theta. Okay, so there we are. Okay, so we don't need to find theta here, because all we need at the end of the day is just cos and sine. Okay, now lastly, before I start now resolving my forces up and down, left and right, I am going to need to consider the acceleration, right? There's acceleration. Now, again, like a slingshot, like a slingshot here, think about it. The man is holding the ball at rest, but what would happen when the man lets go? It's going to move forward, right? The ball's going to push forward. So you can expect the particle here to accelerate upwards. Okay, again, maybe it might go down, I don't know. Again, my final answer will tell me if I'm correct or not, but let's assume the acceleration acts upwards. So now if I now resolve up and down, so firstly if I resolve up and down, so my upward forces is here, so it's t sine theta and another t sine theta, so it's going to be 2t sine theta, two lots of t sine theta, that's going to equal the downward forces. No, sorry, it's going to, and then I'll take away the downward forces, sorry, so that's going to take away the 2g to equal mass times acceleration. Now the mass is 2, so it's going to be 2 lots of a, right? Okay, so hopefully happy with that. Okay, so I looked, so because the acceleration is upwards, so I looked at my upward forces, which are these 2 lots of t sine thetas, and so then I'll take away the downward force of 2g to equal 2a. So hopefully happy with this. So now I know what sine theta is, again thanks to the SOHCAHTOA here. That's 4/5, so it's going to be 2t lots of 4/5. Take away 2 lots of 9.8 to equal 2a. Therefore, well, 2 times 4/5, that's going to be 8/5 lots of t. Take away 19.6 equals 2a. Okay. Now, I want to find the acceleration, but in order to do that, clearly I'm going to need to find t. Well, I can use Hooke's law for that, can't I? So I also know that t is lambda x over L. Okay, there are 2 ways you can do this. Okay, as I discussed at the start when setting this up, the string is essentially in 2 parts, right? And so we've got the left part A to P, P to B. You could consider just half the string. So you'd need the half the extension and half the natural length. Or again, you could just consider the whole thing. You can consider A to P and P to B. So you're considering the total string. Okay, so let's consider the total string here. Okay. So the total string, so my T force, that's going to equal, well, my modulus of elasticity, which is 20, times the extension. Now, the total string, the extension overall is 0.6, okay? Again, if we were to consider just half the string, that would have to half the extension, right? And then the natural length is 0.4, right? So if we work that out, we get my tension to be at 30. Okay, and there we are. So now I can substitute that into here. So therefore I get 2A to be 8/5 of T, which is 30. Take away 19.6, and that will get me 2A to be 28.4. Okay, therefore A is going to be, if I divide that by 2, I get 14.2 meters per second squared there. And there we are. And again, I keep emphasizing this, but the acceleration is positive, which indeed means the acceleration is upwards. So the particle is going to bounce and spring upwards. Okay, so there we are. And so it says state the direction. Well, the direction's upwards. So the direction of the particle is upwards. And there we are. Okay, so we're going to be looking at a few more problems. Okay, so here we're told one end of a light elastic string, natural length 0.5, modulus of elasticity 20, is attached to a fixed point A. The other end of the string is attached to a particle mass 2. Particle held at a point 1.5 meters below A from rest. Firstly, find the initial acceleration. Okay. So again, the situation here, we have a fixed point A, and I'm told the particle is 1.5 meters below A. So it's going to be hanging from a sort of ceiling, right? Like this. So this is A, and then this is the particle at the other end of the string here. Okay. Now, again, I know that this length is 1.5, so the length of the string here is 1.5 meters. Now, that means I know my natural length is 0.5, so my natural length is going to be somewhere there, which means it has to be a stretch. Okay, the string must be being stretched here because the length of the string is increased from 0.5 to 1.5, and so that tells me my extension is 1. And so what that also tells me is that the string has to be stretched downwards. It's stretching down because of the particle at the end of it, stretching it down. So there's a tension force acting up the string. And so there we are. And then, of course, the particle have its weight. Now, the mass is 2, so it's going to be 2g acting down there. Okay. And those are all my forces. Lastly, we need to consider acceleration. Now, again, I could assume acceleration's up or down. Let's assume, well, the particle's going to ping back up the string. So if the string is being stretched, it might want to then ping back up. Let's assume the particle goes up, okay? So if I now resolve up and down, my upwards force is my tension. Take away the downwards force of 2g. That has to equal mass times acceleration. Mass is 2, the acceleration's a, so 2a. Okay, so there we are. We can also again find t using the Hooke's law. So t is lambda x over L. So t is, well, the modulus of elasticity is 20 times the extension x. Now the extension is 1 meters, right? Divided by the natural length 0.5. So therefore my tension is going to be 40, right? And there we are. So now I can substitute that into this equation here. So that means 40 for t, take away 2 lots of 9.8 for g is 2a. If I simplify this, 2a is 20.4. So therefore my acceleration is going to be 10.2. Okay, and there's my acceleration there. And again, it's positive, which means indeed the acceleration is upwards. Okay, and to remind you, if you assume downwards instead, maybe you assume the particle will go down, you'd get an answer of negative 10.2. So you need to flip the direction to make it positive. Okay, so indeed it's upwards. So there we are. Okay, then in part B, now this is where it gets a bit different to the other questions. We now need to find the length of the string when the particle reaches its maximum speed. So now there's some movement going on, okay? So as we discussed, the acceleration is upwards, so the particle is going to move up. So as the particle moves up the string, what point does it reach the maximum speed, okay? Right. The key thing here is, again, maximum speed. That means if it's maximum speed, emphasis on the maximum, that means acceleration is 0. So there's no acceleration. Okay. I tend to think of it because if it's a maximum speed, again, I know that if you think back to normal maths, you should know that acceleration is the derivative of speed. So if it's maximum speed, that means that, well, the derivative has to be 0 because it's a maximum, right? Well, if the derivative is equal to 0 and a is the derivative, well, therefore a equals 0. Okay, so, and that's just how I remember it. I just think of it in terms of like derivatives like that. But ultimately, you do need to know the maximum speed is when there's no acceleration. Okay, 0 acceleration. So, if I redraw the scenario, now as I discussed, the particle is now going to move up the string because that's where the acceleration is acting. So it's going to look something like this. Okay. Again, it's still going to be hanging down. We're still going to have a natural length of 0.5. Okay. But the particle is going to be further up the string compared to the start. So the extension is going to be different. Okay. Yes, the natural length's the same. Because that's sort of like the original length, right? But the extension is going to be different because the particle's further is at a different point on the string. Hopefully that makes sense. Okay, so so the extension is going to be different. Again, we assume it's going to be a stretch, so that means tension is going to act upwards because stretch would be downwards, right? So that means the tension will act upwards, and again the weight will act downwards. Now the weight is 2g. Now I do know for definite that the tension has to act up. Okay, not down, because you might think, well, what if it's being compressed, right? What if the string goes so far up the string, it starts to compress it instead? I know for definite because, as I discussed, the acceleration is 0, which means if I resolve up and down, T, the force in the string, has to equal 2G. So they have to be in opposite directions for the acceleration to be 0, okay? So the forces have to cancel out for that to happen. So indeed, well, I know for definite the weight has to act downwards, so therefore the tension has to act upwards to counter it to 0. If that makes any sense. So if you have any confusion about that, that has to happen, okay, for the acceleration to be 0. So T has to equal 2G. Okay, well, there we are. Well, T's 2G, so T is going to be 2 lots of 9.8. So that's going to be 19.6, okay? But they've asked me to find the, what did they ask me to find? The length of the string. Well, the length of the string is going to be this whole length here, right? So the original 0.5 and the extension X. Now, to find X, I can again use Hooke's law because I know what the tension is. So T is lambda X over L. So therefore 19.6 is going to be the modulus of elasticity, which is 20 lots of X over the natural length of 0.5. So that would mean 20X is going to be 9.8. So that means X is going to be 0.449. Okay. And there we are. Okay, so that's my extension. So X is 0.49 here. So that means my total length in this case is going to be 0.5, add on the extension 0.49 to get me 0.99. Okay, and there we are. That's my total length there. Okay, so we're going to finish off by looking at an exam question. It's the first exam question actually we're going to look at in this chapter. Okay, so here we're told a light elastic string, natural length L, modulus of elasticity kmg, has one end attached to a fixed point A on the rough inclined plane. The other end is attached to a package of mass M. The plane is inclined at an angle theta. The package is initially held at A. The package projected with speed root 6gl up the slope, and first comes to rest at point B where AB is 3L. The coefficient of friction is 1/4. We need to find the acceleration of the package the instant it starts to move back down the slope from B. Okay, now the first thing to note is that actually there was a part A to this question. We can't do part A just yet, but actually we deduce from part A that K is 15 over 26. So here, so the modulus of elasticity is actually 15 over 26 mg. Okay, so that was what part A was asking for. Now for part B, it's asking for the package as it moves down the plane from point B. So let's sketch the scenario. So again, as you can deduce, we've got this sort of slope again, right? Theta. Now, originally the package is held at a point A and it's projected up the slope. So you can imagine A, which is my fixed point. So the string is going to look like this. So we have A here, and the string is going to go up the slope to allow the particle, which they call the package here, to move up. So that's the setup here. Okay, so hopefully happy with that. So the fixed point has to be down the slope in order to allow the particle to move up it. Okay, so there we are. Now we're told so this is the point B, okay, and we're told the distance AB is 3L. Okay, right. It's held at A and then it goes up to the point B here. Then we're told it comes to rest, and then we need to find the acceleration as it comes back down from the point B. So the idea is it goes from A to B, the particle, and then it's going to come back down from B. So we're going to need to find the acceleration as it moves down the slope from B. So we need to find the acceleration, and we know for definite the acceleration is downwards here because it tells us the particle is moving down the slope here. Okay, so there we are. Now in terms of forces, well, again there's going to be a force of the particle. That's going to be well, the mass is m, so it's just going to be mg. Again, we're going to need to split up the I'm going to move the acceleration here. Don't know, the acceleration here, okay? And so there we are. Again, we're going to need to split up my weight then. So this is this is theta. So down here it's going to be mg cos theta, and there mg sine theta. Okay. Then it's going to have a reaction force R. Okay. And then what about the force in the string? Well, the total length of the string here from A to B is 3L, right? 3L. Now the natural length is L, which means it has to be extended, right? Because it goes from L to 3L. So that means it's been stretched. Okay. So let's say this is my natural length L. Then it has to go. Then the extension is 2L. Okay. Hopefully happy with that. And so then you can imagine then the string is being stretched, okay, to the particle. So it's been stretched upwards, which means the tension has to act down the string like this. Okay, there we are. And the last force we need to consider is the friction, because there's also friction involved. Now the friction again acts on the particle. Now the particle at this point is moving down the slope, which means to oppose it going down, the friction is going to have to act up. Okay, so there we are. So those are all my forces. Okay. And so there, hopefully happy with the diagram, hopefully happy with the situation here. Okay. So let's proceed with resolving. Firstly, let's resolve perpendicular in this direction. So therefore I can deduce that the reaction force R is going to equal this mg cos theta acting the other way. Okay. So that means R is going to be mg or mg cos theta. Now I'm going to need to find an expression for cos theta, but I know that tan theta is 5/12. Again, if I now draw a little triangle, well, according to this, the opposite is 5 and the adjacent 12. If you do a bit of Pythagoras, so 12 squared and 5 squared rooted equals 13. We get 13 for the hypotenuse. Therefore, cos theta is going to equal the adjacent 12 over the hypotenuse 13. We can also deduce sine theta from this. So that's going to be opposite, which is 5/13. Okay, well, cos theta is 12 over 13. So I can multiply mg here by cos, which is 12/13. Well, simply R is 12/13 mg. Now I'm going to leave it in terms of m and g. I'm not going to say g is 9.8. I probably could do, but I think just leaving it as letters will help me. And you'll see things cancel in the end. The letters will cancel out. But let's leave it like that, okay? R is 12/13 mg. Then we're going to also then look across the slope, so up and down the slope? Well, firstly, the acceleration is downward, so let's treat down the slope as the direction we want to look in. So firstly, the downward forces. Well, firstly, we've got my tension, and we've also got this mg sine theta here. Okay, but then in the other way, up the slope is F. So we're going to have to take away F, which is opposite direction. And that's going to equal MA. So the acceleration times mass, that's going to be equal to MA. So there we are. Okay. So obviously then, to find the acceleration, we're going to need to find T and F. Okay. Okay, well, firstly, I could find T using my Hooke's law. So that means T, when my modulus of elasticity is 15 over 26 mg times the extension. Now, the extension is 2L here, right? Hopefully you can see that. There we are. The extension is 2L over the natural length, which is just L. Well, actually, you can see the L's cancel here. So we're left with T to be 15 over 26 mg times 2. And so if we work that out, 15 over 26 times 2 gets me 15 over 13. So we get 15 over 13 lots of mg for T, okay? Hopefully you can see that. Again, there's a bit of algebra here. There's a lot of letters, but it's just algebra, right? Don't be scared by the letters, okay? We do the process in the normal way, okay? So now we've found T. Then we're also going to need to find the friction F, but of course we know that F equals mu r. Now we're also given the coefficient of friction, which is 1/4, okay? So that means the friction F is going to equal 1/4 times the reaction. Now the reaction is 12 over 13 mg. So if we simplify this, 1/4 times 12 over 13 is 3 over 13 lots of mg, and that is my friction. Okay, now I can substitute these numbers into here, so I know therefore that MA is going to equal T, which is 15 over 13 mg. Add mg sine theta. Now we know that sine theta up here is 5 over 13. Take away F. Now F was 3 over 13 mg. I don't have any room for this. There we are. Okay, 3 over 13 mg. So if we simplify this, we get MA to be okay. Well, we can add all the mg's together, right? So we have 15 over 13. Add 5 over 13, take away 3 over 13. Okay, so in total we have 17 over 13 mg. Okay, well there we are. So that we can therefore, if we divide by m, okay, we can divide by m. Therefore we just get A to be 17 over 13 g. Okay, and that is my acceleration. Okay. And there we are. You could, if you wanted to, I guess you could give it as a number. If you took G to be 9.8, if you times that by 9.8, you get 12.82 meters per second to 2 decimal places. Either answer, I think, should be fine. But there we are. Okay. So there. Cool. Okay, so that's all the questions. Hopefully that has helped. But I'll see you next time.